Welcome to my presentation on the configuring point-to-point VPN tunnel. I'm doing this presentation to demonstrate how you can achieve a point-to-point virtual private network on top of BGP. And the reason I'm doing this presentation is because VPNs, tunnel VPNs are now coming into the market, and I have seen that a lot of vendors have been advertising it for even household consumers, not just to enterprise. So this presentation here is to show how to configure point-to-point VPN tunnel using on top of a BGP. And point-to-point tunnels are actually really very good because of their scalability. The reason they are also good is that you don't need any permission from the ISP in order to configure them. All you need to know is the public IP address of your local routers. That's all you need to know. If you know the public IP address of your local routers in both connection points, you should be able to configure a tunnel and also encrypt your traffic between the two. So without much ado, I would like to explain what this topology that I have here, what I call boilerplate. Basically what I have is a BGP running through the interfaces, up all the public interfaces. The only interfaces that are not participating in the BGP are the private networks, which is the networks that are adjacent to the switch. For router 1, the 192.168.100.0 network is not participating in the BGP, and for router 4, the 172.16.100.0 network is not participating in the process. So before we start the configuration, I would like to have a continuous ping on one of the PCs, and you will see what happens as the configuration goes on. So we are on PC1, we are on PC2, so we're going to ping PC1 from PC2, which is 192.168.100.1. Because it's a continuous ping, we just add -T. Oh, I didn't put the ping command in front. You can see that the ping will be failing because there is no routing protocol connecting the two PCs. If we configure the tunnel and we add a routing protocol to it, you can see that the ping will begin to succeed. So without much ado, let's hop into the routers and start our configuration. So we start from router 1 first. On router 1, we go on our configuration mode. We do an interface tunnel. We give it a number, and we add an IP address to the tunnel. I have already pre-selected an IP address that will be added to the tunnel. It is this 10.10.10.0 network /30. Because it's point to point, you just need 2 IP addresses to connect them. So we will add the address 10.10.10.1, and the subnet mask will be 255.255.255.252 because it's a /30. And we would add our tunnel source. And for tunnel sourcing, you can either use the interface ID or you can use the IP address on the interface. Here, I would use the interface ID. So we use the F0/0. That is our source. It's F0/0. The interfaces are not showing, so let me just bring them up. Let's go to View, Show Interfaces. I just happen to know that the internet interface facing the internet is F0/0, and we will configure our destination, tunnel destination, and the tunnel destination would be the public IP address of the other parts or other side of the tunnel facing the internet. So the tunnel source would be the IP address here, and I just happen to know that it's 30.30.30.1. So 30.30.30.1, and you can see the tunnel come up here. I would like to put a keep alive here so that the tunnel will be down until the other side of the tunnel is configured. So the tunnel should come down now. You can see that the tunnel is now down. As soon as we configure the other side of the tunnel, it should come up. So we should hop on router 4 and do the same thing. Interface tunnel, give it a number, and we assign it an IP address. The IP address is 10.10.10.2, and the subnet mask is 255.255.255.252 because it's a /30. The tunnel source is this interface here, which is the interface on the router facing the internet, or you can even add the IP address, but I would like to use the interface ID, so it's F0/0, and the tunnel destination is the IP address on the other side, which is on router 1 facing the internet. So that would be 20.20.20.1, and the tunnel should come up. You can see that the tunnel is up, and if we go on router 1 and we check our tunnel, you can see that the tunnel is back up. It's showing that the state of the tunnel has been up. And if we exit on router 1, if we end here and we ping the other IP address of the tunnel from the router 10.10.2, we should get connectivity. So it means there is now a tunnel that is connecting router 1 and router 4 over the BGP. So in order to connect the tunnel with our private IP address, we have to configure a routing protocol to do that. And you can use either any routing protocol at all of your choice. You can use ERGRP or RAPE or even a static route. But for this particular configuration, I would like to use OSPF to configure it. So we go on router 1. This is router 1 here. We configure OSPF. We go to the configuration mode, and we say router. We give it a process ID of 100, and we advertise the networks on the router. So we first advertise the tunnel network, which is 10.10.10.0, 0.0.0. The wildcard max is 0.0.0.3, because the wildcard max is just the inverse of the subnet max. So it is 0.0.0.3, because if you subtract the subnet max from all 255s, you get 3, because the last octet will be 252, and 255 minus 252 is 3. So we give it area 0 here, and then we advertise the private network on router 1, which is 192.168.100.0, and the wildcard mask here is that router 1's private IP address use the /24, so it will be 255, and the area here again is 0. So that is the OSPF configuration here, and we will go on router 4 and do the same thing. So we would end here, go in the configuration mode, and we would configure an OSPF route, process ID 100. The process ID doesn't matter, it can be different process ID, but they have to be in the same area. So we advertise our networks. We advertise the tunnel network on the router, and the wildcard marks again is 0.0.0.3, and they have to be in the same area 0. And then we advertise the private network as well. You can see that adjacencies are beginning to form between the two routers. It is forming adjacencies into the tunnel, so you can see that it is learning about the 100.2 network. And we advertise the private IP address on there, so that will be 172.16.100.0, and the wildcard marks is 0.0.0.255, and it is also in area 0. Oops, I think we didn't put the 0 there. Okay. Having done this, we should be able to ping between the private IP addresses, or if we go to the continuous ping that we established during the configuration, you can see that the ping is now beginning to be successful. You can see that it was failing, it timed out, and it timed out when the tunnel adjacency came up and we didn't advertise the private IP addresses. And then as soon as we advertise the private IP address on the other side of the router, you can see that we are beginning to get a connection here. How we know we are getting a connection is because we have our sequence number, we have our time to leave, and we have the time that it takes for the PC to reach the other side, which is the 44.117. That is why it changes. So yeah, that concludes the presentation of the configuration of the tunnel. The next thing we're going to do is to configure the security part of the configuration. So again, we will hop on, because we are configuring security for all traffics that are going this way and coming this way. We would configure an ICE account policy, and we would also configure an IPsec, and we will configure an access list to define type of traffic that we want into the tunnel, and then we would do a crypto map, and we will apply a crypto map to our interfaces. So let's hop on the routers. This is router 4. I would like to start with router 1 first to avoid any ambiguities. Router 1, we would leave the continuous ping running. So we go on the global configuration mode, and we issue the crypto ICE account policy. We give it policy number 1. We select our pre-share authentication. We would like to select pre-share. You can select RSAs, but we are selecting pre-share. We are selecting pre-share because we want to have a symmetric kind of encryption procedure. In other words, we want the two routers to use the same key to encrypt as well as decrypt messages between the two of them. So we're using pre-share here, and we want to use a hash. And for those who don't know what hashes do, we have different kinds of hashes. We have the message digest 5, which is MD5, and we also have the SHA, the secure hash standard variations of it. So for this configuration, we would use a SHA. And in case you are wondering what hashing does, hashing actually ensures message integrity between the two routers. And how it works is that the sending router would basically take the message into an algorithm and then produce a receipt. And then when the message gets to its destination, the receiving router would also put the message into a hashing algorithm and then produce a receipt and compare the two receipts. If the receipts are the same, the numbers on the receipts or the values on the receipts are the same, then it means that the message is coming from the source that is supposed to come from. If the receipts vary, then the computer would drop the message because the message has been either tampered with in traffic, or it's not coming from an authoritative source. And we would use a Diffie-Hellman group 2. We would use a Diffie-Hellman group 2 here to ensure that our keys are exchanged securely. And we can set a timer here when the processing of encrypted message between the two receiving routers would restart again. But I would prefer not to do it, to leave it the default, which is 24 hours. So at this point, we would exit here, and we would set up our ISACAMP key. So we go crypto ISACAMP key. Anyways, in case you are wondering the meaning of ISACAMP, it simply means the Internet's Security Association Key Management Protocol. That is what it means. So we would set our password here. So let's use Cisco 123, and we will add the address that we are pairing with, which is the address on router 4, which would be 30.30.30.1. And yeah, that's it. So now we would set our transform set. We would go crypto IPsec transform set, and we will give our transform set a name. Let's just give it a transform set. I think I forgot to do one thing here. Yeah, we did not select the encryption mechanism that should be used, but I'll do the transform set, and after that I'll just go and fix it. Transform set, we would, our ESP would be AES, and then ESP, the hash we are using is SHA dash HMAC. Let me see. Yeah, I think we have everything. So that is the end of this. Let's go back to our policy again and basically establish the encryption mechanism that we want to select. So we're going to copy the policy, the initial configuration, and then we would paste it here and hit enter. So we would select our encryption. Basically we are using AES. We can use, there are 3 encryption methods that you can use. You can use DES, triple DES, or AES. AES is the most modern of all the 3, so I would prefer to use AES. And with AES, the default key is 128 bits, but you can also choose 192 and 256 depending on what you want. The higher the bit values, the key values, the key bits, the stronger the encryption. However, the tougher it is on your machine. So I would like to leave it at default. So let's exit here. Let's just do a show running configuration to see that all our configs are correct up to the point that we are. Yeah, you can see that we have our crypto policy. We selected our encryption system, which is IEX. Because we pick the default value, we are not seeing the length of the key. If we had selected any other we would have seen the length of the key to tell us whether it is 192 or 256. Our authentication is pre-share, and our Diffie-Hellman group is 2. And SHA is the default for the hash algorithm, so that is why it's not showing here. And we have our ISACamp key and the router that it is going to, and we also have our crypto map, our IPsec. So the next thing we're going to do is that we're going to define the traffic that we want into the tunnel using an extended access list. So we go IP access list extended. We would name it VPN traffic. I'm using capital letters here just in case if you do a running config, you would see that all the ones that are cap are inputs that you have to give to the router. So we do it like this, and then we would permit the traffic that we want. We are permitting GRE traffic from hosts. The host router is router 1. So the host address is the address that is facing the internet, which is 20.20.20.1, to the destination host, which is the host that the tunnel will terminate, which is 30.30.30.1. That's it. And now, having done this, we can then go and configure our crypto map. So we can say crypto map, and then we give it a name. Let's call it crypto dash map, and we would give it an ID, and we would say that it is an IPsec ISACamp crypto map, and we would set our peer, which is the address that we're pairing with, which is 30.30.30.1, and then we would set our transform set, and we already set up our transform set at the top over there. In our when we did a running config, we even saw it. So this is our transform set. So we copy this, and then we bring it. Oops, what am I doing? I have to delete this. Transform set, and we set our transform set to transform set. I am not copying the right thing here. Copy this and paste it here. Good. We now have the transform set there, and we would match our address. So match address, and the address we are matching to is the access list that we establish, and the name we give to the access list is because it's named. We just copy and paste the name over there. So we are matching it to the access list. We hit enter, and that's it. We are done configuring our IPsec. The next thing we will do is we would apply the IPsec into our interfaces. So first we would apply it to the tunnel interface, tunnel 0, and we will say crypto map, and we would add the name that we pick for it, which is crypto map. Copy it and we paste, and then we would add it to the interface that is facing the internet, and I happen to know that it is interface F0/0. We will do crypto map, and we would add the name of the crypto map that we set up, which is crypto dash map. So that concludes the configuration for our all the configuration for router 1. You can see that we are beginning to get messages that our OSPF adjacencies into the tunnel has failed, is down. It is down because we have set up a crypto map on an interface without attaching it to, without a corresponding interface. So what we do is we will go to router 4, and we will do the same thing. This time I will not talk, I'll just do the config. Pre-share encryption that we want to select is AES. We are leaving it at the default. We want our hash to be SHA, and we want our Diffie-Hellman group to be 2. And we will exit, and we will set our ISACAP key. And I know that we selected Cisco 123, but to avoid any mismatch, we should just go and copy it from here, from router 1, and bring it to router 2. So we just copy this and bring it down here, and see this, the address is Cisco 123. Yeah, and the peer address that we are matching it to, because this is router 4, we are matching it to 20.20.20.1, which is the address on router 1 facing the internet. And now we can go and do our IPsec. So we will do crypto IPsec and transform set. We would call this transform dash set. Okay, we will do our ESP. We're choosing AES, and we'll do our ESP here. We're choosing SHA and HMAC. And now we can do our access list to define the kind of traffic that we want into the tunnel. So we do IP access list extended, and we name it VPN traffic. These names do not have to match with the other router. The only thing that have to match is the crypto map password and the matching addresses. And we are permitting here GRE traffic from host 30.30.30.1 to host 20.20.20.1, and that is the end of it. We will then go and configure our crypto map. And we would call it crypto. The name doesn't have to match with the other router. Map, we give it a number, and we would say that it's for IPsec and ISACAP, and we will set our peer. The peer is 20.20.20.1, and we will set our transform set, and we already configured the transform set here, so we just go and copy this name here and bring it down here. And now we would match our access list, match address, and the address will be the named access list that we configured here. So now have the name of the access list, copy it and paste it, and that concludes the setting up of our crypto map. The next thing we'll do is we'll just go into the interface tunnel 0 here, and we will just add our crypto map. The name we gave it is crypto map, so let's just copy it from the config. Copy, oops, and paste. And we will do it to this, we will do the same thing to the interface facing the internet on here. The internet facing the internet is 0f0/0. So we go on interface f10/0, and we would add crypto map, and then we would add the config that we added. So we paste it, and that's it. Let's exit. Sorry, exit or end. Let's go and look at the state of our ping and see what is happening to the ping that we established at the starting of the configuration. If we go on router 1, we should see that we are now getting all our adjacencies back up. Our tunnel adjacency is back. So if we go to the PC1 and we check our ping, we should see that the pings should start getting successful. You can see that the pings are starting to be successful again. You can see that we're now having a successful ping. Meanwhile, previously it was failing because of the IPsec. Now it is succeeding. The ping is now succeeding. So that concludes our configuration of the VPN tunnel using GRE. VPN using GRE tunnel. And if you want to verify that messages are encrypted, you just go into the routers and see if first we have to check and see whether or not we have an ISA account policy, active as ISA account policy between the two routers. So we just say show crypto ISA account security association. You can see that yes, we do have an active association here, and it is telling us from this place here to the other place, to this other router, and it's active. And if we check, if we do a show crypto IPsec security association, it should show us that our messages are being encrypted and how many of them actually are. You can see that we have 163 messages are encapsulated, and 163 messages are encrypted, 163 messages hash certificates